very important for you to know. Especially since, there's a lot of data that we'll get into in the future, maybe, especially in maybe the fourth class that definitely needs Python training for you to understand. So yeah, once again, as long as you guys hopefully kept some of that stuff fresh, just kind of practice it as you go along, then you should be fine. And feel free to like ask me for problem sets too. I know there's some resources online where you can find ways to kind of train it. Because I know the column thing and the coding thing, that's the thing that really comes with practice. I know like a few minutes before class, actually, one of the code actually bugged out. So I had to go on Stack Overflow and check it. But basically, yeah, keep your eye out. Don't feel bad if you don't get it right away. It's really just a learning curve. But yeah, today is Thursday, and we'll be primarily focusing on a couple things. First of all, looking at sampling and bias in statistics, and also the idea of the hypothesis test. And I'll come back to these later, but these are relatively key concepts. And the hypothesis testing concept is really the foundation of a lot of the stuff that we're going to be doing on the next week's Tuesday and next week's Thursday. So kind of key that you guys, even if you do have prior coding knowledge, it's kind of key that you guys understand the kind of foundation of it so that you can apply it with your code in the future. So yeah, be wary of this is kind of more of a foundational heavy class. So be prepared for that. And don't be afraid to kind of ask questions or come back later, rewatch the recording and check out, kind of ask me through the threads because I'm always there. I've got the email set. So if anyone does anything, I'll see your questions. But yeah, let's kind of start off here. So the idea with sampling, it's a bit interesting because this class specifically was more really about, if you remember in my previous graphic, this specific class was more geared towards the idea of exploring your data. So this is, so we're kind of operating under the assumption that you already had data that you had through a data set or you already got it from a survey before. So most of the tools that we're learning, like the t-test and ANOVA and sort of machine learning, that stuff is really done when you already have your data. So most of sampling and most of those procedures aren't really a big deal when you have your data already. That is something usually to be done on the field. So if you're administering a survey or when you're starting your project, that's when you're actually kind of trying to pay attention to sampling and bias. So if you are a researcher and you are really just working with data that someone else has provided you, and you're really working with the kind of conditions that you yourself are not creating the survey and you yourself are not sampling the people, it's not your biggest concern here. So for those of you who aren't working with this at the moment, this won't be really applicable to the rest of the class. But this is also incredibly important to know. First of all, in just research in general, it's just good practice to know what a good sample is. Because if you remember last time, my example with the mental health survey, that we didn't know how it was sampled. We didn't know, how it was, administered. So we couldn't reliably say that this was good data, and we couldn't reliably, draw conclusions or publish a study on it because we don't know if the data set was somehow biased. So it's important for you in general to just know how to identify and realize where biases could be in sampling and whether your data is good data, because good data will get you good results, but bad data will never, you'll never be able to really fix bad or flawed data. So I think, yeah, it's definitely important for you to keep this in mind. And in addition, if you're choosing data sets, that's also a thing you might want to consider, whether someone else's procedure might be flawed or, if the sample size is too small, etc. So we'll get into that as we go. But first, let's kind of set you up with sort of a basic example on the idea of how hard it is really to do random selection. So you got 4 numbers here, 1, 2, 3, 4. I want you guys, don't type anything in the chat yet, but just choose one of these numbers at random. So which number feels good to you, choose it. Think about that for a moment. And then I think when you got one, raise your hand on the Zoom. Yeah, just go with your gut feeling. So for those of you who aren't really sure, just go with your gut. It's a random selection. Nothing big based on this. All right. So for those of you who have your hand raised, type your number in the chat. Don't look at anyone else's. Don't change your answer. Just type your number in the chat. Ooh, yeah. So look at that. If you look at all those samples, you know, is there something flawed in there? Is it inherently random if you're looking at these selections? Like, no ones. Yeah, no ones. Very few twos. Everyone's very much skewed towards the 3 and 4. So in this kind of thing, you're really just saying it's not really random, is it? Or is it, is this data set that we're looking at, is this flawed or not? So that's kind of really just an exercise in like the idea of how, hard it is to really choose randomness, and really kind of bias in the samples. Don't worry about this for now. But yeah, definitely. Yeah, definitely an interesting thing. Yeah, single two. 1, 2. I'm proud of you, whoever chose two. Who chose two? Michael, my boy, holding up for us. I'm proud of you. But yeah, so looking at this, why does this kind of stuff occur? So not necessarily in this sample, because you guys, it's probably just kind of a chance thing, but really with bias in large surveys and large data sets in general. There's usually two common types, especially in survey-based data sets. It's kind of harder to have bias when you're looking at like bacteria data sets or something like that, because the bacteria can't respond randomly. But there is potential for interference, with some kind of um, issue with contamination or some kind of human error in measurement that is also possible in bacteria sets, but also usually bias is a large thing when you're looking at human response, or when you're looking at the sort of issues that you have with that kind of human selected data. So kind of what you just had. Yeah, main thing here, first of all, selection bias is a big one to know. This generally occurs when a subject or the people answering the study, um, they differ from the population. So maybe your population, you're looking at a group, and then the people that you've chosen, they're not really representative of the like population that you're looking at. Maybe you chose sophomores. You want to look at all the sophomores in high school, but then somehow you chose all the females, or you chose all the people in AP classes. That's probably not representative of your entire sample. That's definitely something you have to look out for and may cause errors. And two ways this also manifests in is specifically in non-response bias. So, if someone, doesn't choose to answer, it's going to take away from the, validity of the data set, of the representation here. And also, this is a big one. This is a big one in surveys, especially. So if you guys are ever going to do surveys, make sure you keep this in mind. The voluntary response bias, you'll learn this in AP stats also. This is a big thing in AP stats. But when you're sending out a survey, and usually it's optional, usually you're banking on your respondents to respond back at their own will. And voluntary response bias really ends up happening when these guys are self-selected. So it's like when you send out a survey into the web, you're like, hey, fill out the survey. And then really only the people who want to fill it out are going to fill it out. That's going to be the reality of, how this sort of happens. And then the issue here really is that it's not often that everyone, like everyone within the skill, not everyone's going to respond. But the people who do respond are probably going to be the people that are either like the most passionate about it, or the most extreme about it, and that's probably going to skew your things. So I remember there's a famous example. There was I think they sent out a survey through the mail, which is also like extreme voluntary response bias, because you can't even just click that and move on. You have to fully package it and mail it back. So you really have to be potentially dedicated to what you're thinking about. But what happens here is that when they sent out this survey, it was about, I think, like, what's your thoughts on, I don't know, like parenting? I don't know, like whether you should be whether you should be married, like whether you should have the dad take care of a kid. It was something like that. And so then they sent it out to a bunch of like housewives. And the survey found out like, oh, like 50% of housewives are unhappy. And that was, but then when they kind of did a general thing, they found like it's much less than that. And so then the reasoning here was kind of most likely the housewives that are the most unhappy are probably going to answer the survey and make their voice be heard versus the housewives who probably don't really care about it as much or are fine. They probably won't be as likely to answer your survey. So once again, this kind of thing you have to look out for, especially just if you can't force, usually you can't force the people to take your survey. So whenever you're sending out something like this, you have to acknowledge that this is a possible, this is a chance that this would, take hold of some of the responses that you have. So yeah, that's selection bias. In addition, response bias. Um, yeah, it's bias that leads to issues with measurement. So instead of like, hey, I'm selecting, a bunch of sophomores, that would be kind of selection bias. That this is more the idea of like the people who you chose when they're answering, or the things that you're measuring, really, there's going to be bias or issues in this specific issue. And so I kind of mean here in this might manifest in, hey, human error in measuring. So maybe you have like a faulty ruler or something. That could be a thing quantitatively, but also more common in the human response sort of surveys and the sampling. What you end up kind of getting is different ways in how people answer the questions that might affect how your answers are collected. So for example, social response bias, also known as social desirability bias, that is really the idea that people might lie or people might not tend to tell the whole truth, or kind of skew their responses based on how they feel is good for the situation. So I think the most largely known example is like lying at the doctor's office, like, hey, do you like smoke? Do you do something? And usually those behaviors aren't really good. When you're at the dentist and they're like, do you floss? How many times do you floss? And then you're really pressured to kind of be like, more than I usually do. So it's this kind of thing where you're trying to over-report on good behaviors because of maybe the surveyor's pressure or something like that. It's the idea that you're trying to like blend in with society, you're trying to give good answers that will affect some things there. And I believe, let's see, what else is there? There's also a possibility, I know there's also an example where if you have, I know sometimes race gets affected. I know there was an example before where there was an interviewer, he was African American, and then all the people he surveyed, they were white, and they kind of changed their answers. So there were there's two reporters. One of them was African American, one of them was white. And then the people that they interviewed the same people. The people that they interviewed changed their answers for the African American respondent, the reporter, versus the white reporter. So it's like small factors that can potentially result in social response bias or something like that. I think more common is the poorly worded or leading questions. That's also, you guys probably intuitively know about this. I think it's the idea that, if your question isn't super clear, it's hard to understand, people might be confused. They might either be less likely to answer your question in the first place or give a kind of I don't know or confused answer. I think there's an example I knew. My stats teacher brought this one up. They were like, I think someone was polling about whether whether people believed the Holocaust happened. And then the study used a super bad question choice. I think it was very convoluted. It was like, do you believe that it is impossible that the Holocaust may or may not have happened? And then something like that, but it was more complicated. And then, of course, I think most of the respondents, there's like 50%, they were like, I don't know. And then like something that was yes and something that was no. But then in a separate survey, they were just very clear. They're like, do you think the Holocaust happened? And then there was a lot less of the denial that you saw in the first question. And this was mainly attributed to the fact that, yeah, the question was badly worded. People didn't really know what they were asking. So keep that in mind in designing good survey questions if you ever are dealing with sample stuff. So mainly this type of bias, these types of things, there's a lot more bias than these. These are mainly the main two that you deal with, especially if you're looking at surveys. But when you're really dealing with bias and selection, be aware that it's pretty common and that you have to kind of either get a really airtight kind of sampling method, or try to work with some some data that might be harder to be biased. I know working with humans in general is very hard because you have to kind of take into account a lot of things. So that's why it's kind of hard to run studies on humans occasionally. But yeah, this is kind of why we really want to emphasize the power of sampling methods here. I'm not gonna talk too much about this because this is actually, yeah, this isn't necessarily the focus of the class because we as a group aren't going to be working with, sampling and all that. So yeah, okay. So I'm gonna show you this video real fast. It's 3 minutes. Hopefully, let me know if the sound doesn't work. But this should be kind of a nice little primer on basic sampling methods here. Oh, I didn't do that. My bad. All right. We're getting there. Yeah, so these are some very basic kinds of, okay. Hold on. Can you guys hear this? Let me know. Yeah, can you guys hear this?
Can't really hear it clearly.
All right, cool. Let's figure this out. Let's see, it's quiet. Ooh. Let's try this. We're experimenting with Zoom today, boys. We're figuring it out.
A sample is part of a population, and researchers use samples to collect data and information about a variable or variables from the larger population. To obtain samples that are unbiased, there are mainly 4 different sampling techniques or methods: random sampling, stratified sampling, cluster sampling, and systematic sampling. A random sample is a sample where every member of the population has an equal chance of being selected. There are a few different ways to do this. The researcher could number each member of the population. To keep it simple, say a population of 90 members. He or she could then place numbered cards 1 through 90 in a hat or bowl or mixer and select as many cards as needed to complete the sample. Or they could use a calculator or computer to generate random numbers. Or they could use a random number table like this one. A stratified sample is where a researcher will divide the population into subgroups to have members from each segment of the population, and a random sample is derived from each subgroup. For example, let's say you wanted to know how much money people saved on a yearly basis. You could have subgroups of people in their 20s, in their 30s, in their 40s, and in their 50s. You would then take a random sample for each of these groups. A cluster sample is obtained by dividing the population into sections or clusters, then randomly selecting one or more of the clusters and using all of its members as members of the sample. This is often used when the population is large or there's a large geographic area. For instance, let's say you wanted to survey small business owners in a very populated city. It would be costly and time-consuming to survey every single small business owner. So you could create a cluster sample using zip codes and maybe survey 2 or 3 of the 13 different possible zip codes. Cluster samples can be efficient and cost-effective. However, there are times when the cluster does not represent the population. A little note, the main difference between cluster sampling and stratified sampling is that subgroups in the stratified sample have similar characteristics, and the subgroups or clusters in the cluster sample are intended to vary in characteristics. A systematic sample is where a researcher will assign a counting number to every member of the population, then select a random number, then select members for the sample at regular intervals from the starting random number that was selected. For example, let's say you wanted to know how much time people living in a singles-only apartment complex spent watching Netflix on a weekly basis. you would want to get, say, a sample of 50 members. If there were 1,000 units in the complex, you could number the units 1 to 1,000 and generate a random starting number, say 234. Since you want a sample of 50, you could divide 1,000, the number of the population, by 50 to get 20, which would be your interval number. So 234 would be selected for the sample, then 254, which is 234 plus 20, then 274, which is 254 plus 20, and so on until you had your 50 members selected for your sample. This sampling method is easy to use if the population can be easily numbered. Another note, even when using the best sampling methods, a sampling error, which is the difference between the results of a sample and a population, can occur. And there is one other sampling method called a convenience sample, where a researcher develops a sample from members of the population that are easy to get or convenient. Many times these samples lead to biased results. All right, my friends, I have more videos right there for you. Till next time.
There we go. Thank you, King. So, all right, so hopefully everyone got something out of that. Yeah, the main thing here, really, there's a lot of ways that you can do sampling and stuff. It's not necessarily the biggest, you don't have to memorize this stuff unless you're really trying to take AP stats or anything. It's not the biggest, stop doing that. But yeah, it's not the biggest concern here. Especially in this class when we're really just looking at, hey, if you have data already, it's good for you to know. Ooh, Derek, that's a good point. All right, you start at 234 and go up by 20. Yeah, that's yeah, it's you might have to look at how a random number, like the charts work out, because there's a way that they kind of go about this sometimes. Yeah, you can, I think, yeah, I'll put this presentation and the link and everything into the drive later too. So if you want to revisit this and check it out, yeah, you guys can debate this in the chat if you really want to. Not my biggest concern at the moment, since sampling was never really my biggest, my thing. I don't really carry out surveys or anything. We briefly learned this for AP Stats. So if you guys are taking that class, look forward to learning, differences between cluster, stratified, random. But basically the general rule of thumb is just try to get a simple random sample. And that's usually the best representative sort of thing for your population. It's not usually doable because sometimes it's hard to, it's like if you're surveying the entire United States, it's really hard to get a simple random sample that's representative. But in the best case scenario is always trying to get that. So using stratified, using cluster, using those random number tables, the whole point is really just trying to get as close as possible to a perfect, simple random sample. Like the best case scenario is survey the entire population, which is just the entire, like, hey, population of the US, that's the whole thing you want to look at, or the population of the world, you're looking at humans. That's the best case scenario, but usually not feasible at all. So, we can only hope, we can only try. All right, but so yeah, hopefully one thing you can take away from this, though, we will get to this one, is that the thing that really affects us, I think, in our exploration of data sets is the idea of like the sample size. And I did touch on this in the first class, I believe, and those of you who do math, probability examples, things like that, you're already probably aware of the law of large numbers. And so, yeah, we're gonna explore this a little bit more. I think it's a good thing to know, just as like a fun tidbit of statistics, and also in, really understanding how to choose good data sets, because I know some people, a lot of people that survey, they make a lot of, mistakes in thinking, oh, 20 people's enough or 50 people's enough. But it's really the idea that the bigger your sample size is, and this is kind of intuitive, but it's really the bigger your sample size is at the end of the day, the better your data and the better your results might look. So it's more likely to be valid or applicable, more likely to be true. So we're gonna kind of take a look at this real fast, just because we have a bit of time here. So if you remember the drive, for those of you who don't have the drive link, I'm gonna grab it for you guys. Put it in the chat real quick. Yeah, reminder here, all this stuff, it's in the ed thread. So if you guys lose it and want to come back later, feel free to grab it. But basically, this is the folder we're working out of. Should probably organize this in folders by day, but for now, we're going to work with this. So survey.csv and the introduction to Python, that was stuff in day one. If you guys missed stuff in day one, feel free to check back on those. This is mainly class notes, and this is the data set that we worked with in that class. So you can always come back and check out the things that we wrote here. But for today, for now, we're going to be touching on this stuff later, but for now, we're going to be looking at this law of large numbers collab. So come with me here. We've got a nice little little exercise for you guys to start off with. So yeah, does anyone, before I get into this, does anyone already know what law of large numbers is? So you could share it in the chat if you want, but let's see. All right, Derek, let's go. Google is your best friend. So honestly, that's probably, that probably counts as prior knowledge now. But yeah, it's law of large numbers. It's like, it sounds like a fancy word, to be honest, but it's not really like a whole theorem. It's not like Pythagorean or anything. It's not knowing in like big, linear algebra or anything. It's really just a fancy way of kind of going about probability and going about stats. So yeah, here you can kind of explore it a bit. So you can kind of get started here. For those of you who want to follow along, as always, feel free to, if you never worked in Colab, feel free to click on it and then it'll bring you, if you click open in Google Colab, you can open your own copy and then write whatever you want. It won't affect my master file, so you can feel free to explore and change whatever you need. But yeah, I'll be working from here for people who don't have access to their Colab or anything right now. Yeah, hopefully, yeah, I think, yeah, if you have trouble with your Colab, let me know, it's fine. But yeah, you should be able to kind of run it at your leisure. So yeah, we can try it out. As always, I got your packages here. I don't think this is necessary for this because I don't think any of them use NumPy. I think I had it on here when I was debugging, but it's good for you to remember that. So let's see. Okay, so let's kind of start out here. A very big example of law of large numbers, I think, you can kind of see in the idea of polling and the idea of elections. And we all have been through elections, so it's you're pretty close to home here. Well, yeah, let's try this out. So let's say it's an election day. There's 100,000 voters in a county for a election for the president. So let's just kind of make a mock data set, just kind of like a pretend little thing. So let's say your population, I'll run through this code. You don't have to know how to code this, by the way. This is just me setting up a simulation for you. Those of you who love Python and those of you who want to kind of get better at Python, feel free to, I'll run it through for you guys. But yeah, don't feel pressured to have to memorize how to create this stuff. Oh, Emily, yeah, it's okay. But yeah, so let's kind of basically the idea of this is just, hey, you have your population of 100,000, and let's say there's two parties, A and B. So there's, in the population, I am God and I know all of this stuff. In the population, I know that 51% of the people in this county are in party A, and all the 49% of people in party B exist in the population as well. So these are the absolute sort of voting like demographics. That's probably, assuming no one branches out from their party, this is probably the way that their voting lines are going to go. So through this thing, you can kind of estimate, hey, the amount of people in the population. This is intuitive math. The population times the percentage, that's going to be your sample, like not the sample, the amount of people in party A in your county, and this is going to be the amount of people in party B in your county. that's pretty intuitive. You need the NumPy package for this, so it just does a thing. But here, what you can kind of do is that if you multiply, this is just a fun little Python thing. I don't think I introduced this to you before, but if you multiply a string by integer, it will it will basically make multiple like variations of that string. So if you have a times 3, it'll do like 3 a's. That's what'll happen here. So what you can do is, hey, if you have a times the amount of a people, so let's say like, whatever this was multiplied by, you'll get that many a's, and then you can get that for that many b's. And if you add those together, you're going to get this nice little list for that. So, ooh, Angela. Okay, yeah. Okay, that's basically, don't worry about that. Basically what that means is like usually usually is the case if you get a random like Colab notebook by some random internet stranger, Google will try to warn you that there's a possibility that this is like a virus or anything. I didn't put viruses in this thing, so you don't have to worry about that. So just like if you yeah, I can verify. Don't think I put viruses in this notebook. Everyone's been using it perfectly fine. So yeah, you're fine. As long as it doesn't interfere with like running it, I think it doesn't really matter. But Google likes to keep you safe, even if it steals your data. But that's fine. But yeah, so once you can add those things together, it'll basically kind of create this this sort of list, or this vector per se, of a bunch of A's together and a bunch of B's. And what this does basically just shuffles this a bit for you. So here you can just shuffle this, and what you'll get at the end is this great like population of people. So these are A, B, A, B, A, B. Maybe these are by street names. Maybe these are by houses. Like you live in B. This is A. This is A. This is B, etc. So yeah, this is basically. I'm not going to scroll through it, but this is your population per se. So in the population, usually leading up to the election, you're like, hey, let's try to gauge the people who want to vote for what. And so then usually NBC or someone or Fox News grabs like a sample or, kind of a thing to poll people on what they'd like to vote for. And then, you'd get something of a prediction per se. Oh, wait, let's see. So I'm gonna have to check that in a bit, but I don't know, we can try without NumPy. I think I put it in there for a reason, but yeah, I guess you don't need it. I think I had a tidbit in there that we used it for. Yeah, you don't need NumPy, but I think there's a fancier way you can go about it in creating something with NumPy, but we're not gonna go into that right now. But yeah, so I think you do use random here for the random.sample. I think usually in packages, they'll like put the package name here and then dot whatever the function is. So that's usually a good thing to know. So like, when you're using pandas, it's like pd.dataframe, not PDF. pd.dataframe is a thing in pandas. So yeah, usually they put the package name dot something unless it's very universal or it's very like, something like that. But usually that's how you can probably tell. Yeah, but good eye. So yeah, I probably deleted the NumPy code there. But yeah, so let's say we have a population already. Let's mimic the process of collecting a random sample. So yeah, let's try this. We're going to pick a random number of voters and we're going to survey their votes, assuming that they vote with their party lines. So, let's say your sample size, you want to pull 1,000 people out of your 100,000 population. That's going to be your sample. So you can use your, I believe it's still import random here. You can use your random sample. And basically shuffled total is this population, if you remember. So out of shuffled total, we're picking 1,000 people. And it's going to basically, when you print this, here is 1,000. As you can see, this cursor is bigger than this. So you can kind of tell this is going to be 1,000, the population of 1,000 that we grabbed, etc. So here you can count this actually with the counter. And what this will get you is basically the amount of people that said A and the amount of people that said B. You have 504 people who said A and 496 people who said B in your population. So, not the population, in the sample that you grabbed. So the 1,000 people, that's how many there. So we can try to calculate something of a, a ratio here, a percentage. And so if you have your A over the total, 1,000, prevalence of A is 0.504 and the prevalence of B is 0.496. And that's, that's pretty close to whatever you've got here. It's kind of, it's a few decimals off, but that's kind of to be expected. But hey, that's kind of, that gives you a pretty close insight to what your population percentages is. But let's try this. Let's narrow that sample size down. Let's go very extreme. Only 10 people. We're only sampling 10 people in the entire 100,000 people. So once again, do that same thing. And then let's see, because it's probably, well, we could try this here already. If you have a sample size of 10 and you run this thing, wow, well, those are close somewhat, but it's still much more far off than you see for like this stuff. Like it's, A's still on top. That's still a thing, but it's not as accurate as when you had 1,000 there. So like if you keep going here, there's a possibility, hey, this is equal now. That's not, that's not that good. And, if you keep going here, wow, that's definitely not representative. So it's really kind of shows you that kind of impact you have with the idea of this. So if you keep going, actually, so this is, if you run it separately, so here what you can do is you can repeat it, like say 100 times to get a distribution of like how often your ratio is, so like how often A hits 0.8 and how often B hits 0.2. So like what happens here, if you run the for loop and repeat it 100 times, what you end up getting here is this sort of table. So this is like basically 100 iterations of me running this thing. Here, yeah, some of these, like, hey, A is losing here. That's not what the population has. And then here, A is very much losing versus here it's winning. Here it's, it's at that kind of same old, sort of close, not really close. Yeah, that shows a lot of variability, especially in such a small sample here. So let's say you can plot whatever this is here using Seaborn. So this is a SNS.dis plot. It plots the distribution. You can come back to this code whenever, but it's really using this data frame that we had here and then trying to get what you had. So this is the ratio for A in the samples. So this is whatever A was. And here you can kind of see, hey, it's, it's not that great because it's like, yeah, sure, it kind of falls into, if you run it a lot of times, you're going to get something close to this because that is the most common like pick. But here you see a lot of extremes still. You got A winning a lot actually in 0.8, which is really not close to the population. So it really just demonstrates a lot of variability. But then, yeah, if you try it with the sample size 1,000, which is, once again, that was the size where the percentages was actually pretty close to whatever the population was. Say you run that 100 times. First of all, you check this out. Yeah, it's still pretty close. Yeah, sure, it loses here a bit. But once again, it's all in that kind of similar range versus what we saw up here with, 7 and 3 and 8 and 6 and whatever was going on over here. It's definitely a big change because it's definitely at least closer in value to what the population is reflecting. So if you were to graph this based on A, what you actually see here, sure, it looks very, severe as well compared to this, but actually, if you look at the values, the variability is much smaller. So you're really only going from 0.48 to 0.55. And when you consider that A's true thing was 0.51, and it's pretty big here, yeah, you can kind of get the idea that this is much more accurate when you're sampling to reflect the population. And if you keep going, let's say you up your sample a bit more. This is a 10,000 sample. That's like almost like you know, that's a decent chunk of the population that you're looking at. If you run this exact thing, you're going to see, I think, that it's going to get even closer. Hey, look, most of this stuff is going to show that A is winning now. That's definitely what we want because that's in the population. Versus over here, it wasn't as accurate there. But here, you can get a much better distribution with where A is. And here, it's even going to like, it's definitely most of this stuff, it's over like 0.5 now, but it's really getting into, you know, tenths place, thousands place, hundreds place. So it's not as variable to change. And thus, the basic idea here is really just that it reflects the population more. It's a better reflection of how the population is working. And then, you know, up there, the sample size was kind of like the distributions, the percent was really 51% versus 49%. That's like very close. But hey, if you have the parties have a larger difference. So let's just say people in party A, there's like 80% of people in party A up here, and there's like 20% of people in party B. That's a much bigger difference. So if you run the same thing, once again, don't need NumPy. Thanks for pointing that out. But run the same thing here. Hey, yeah, definitely a lot more A's in the population. But then here, maybe you need a smaller sample size to kind of derive the real estimation because it's a bigger difference and you're kind of less likely to get super skewed results. So once again, 10 is never ideal as a sample size, but here you can see it's more accurate in how it's kind of reflecting things because of the inherent population difference is so like big. So you can usually most of the time sample a pretty good thing. You still have issues here, 50-50, not what's going on at all. But yeah, but still rule of thumb is still, hey, as long as your sample sizing is increasing, it's gonna get more accurate. This is like for A, it's definitely more accurate. It just went from these large changes to just kind of minute changes here. So, and it's really kind of nailing that 0.8 versus here, it's having trouble identifying between 0.7 and 0.8 there. So yeah, that was a lot, but there's a lot of code mainly that I was walking you guys through. But mainly the whole purpose of this was the idea that, yeah, it's really the idea that you're not looking, when you're doing your samples at least, or at least even if you already have the person sampled, it's just good, it's good knowledge to realize that if you're working with a data set that's bigger or you're working with a sample size that's bigger, it's just good for you to know that it's, you know, there's more you could do with it. So let's see, got roughly 45 minutes. So I'm gonna go through with this and then we'll see if we have time for a break or not, because there's a lot of stuff I'm throwing you guys on and I want to make sure that you get this part. So yeah, lesson with the first part, basically, if you don't want to retain all of that law of large numbers thing, just know bigger sample size is better. Watch out for simple random sampling, try to achieve that, and be careful with bias in your data set. That is basically your issues in sampling and your issues in getting data. And that's pretty much the extent of what we'll cover in the class. If you have other questions, feel free to ask me about it later. But for now, we're going to move on to actual exploring the data once again. So hypothesis testing, this is really, we covered descriptive statistics in the first class. This is now inference statistics territory. So this is really the idea of testing a hypothesis and like really seeing if you have significant results. Before you could really just kind of see the data, but this can like prove whether there's the pattern in the data or, you know, the difference in the data, whether that is a significant result that you can kind of present and draw conclusions from. So this is a pretty important part of statistics, and also really the main way how people explore it with the tools. I know people like to visualize, but this is how you can really prove things. This is how you can get evidence and all that. So this is really the whole foundation of everything. There's different ways you can hypothesis test. There's different tools. There's different things. I know I just threw at you before, t-test, ANOVA, chi-square, whatever, but it's all really just inference statistics, and the basis of seeing is your result significant, and then proving it quantitatively instead of just looking at it on a graph. So yeah, these are foundations, and then everything that we talk about after this is just kind of applications and the tools of it. But yeah, it's important for you to understand how it basically works. So yeah, let's kind of go through the overall procedure. And there'll be a lot of examples, so it's all right if you don't get this firsthand. A lot of people had to practice this a lot in stats. It's a second semester thing, actually, so a lot of people didn't even get to that in the first semester. But the idea is this. First, you have some kind of problem, and then usually you have to state a hypothesis. And this isn't necessarily like the science, I believe this will blow up, etc. This is more quantitative in the sense that you are drawing some kind of value, some kind of thing from the population that you believe might happen. You want to test whether that's true. So specifically, you get two hypotheses when you're hypothesis testing. And the name itself is hypothesis testing. You're testing if the hypothesis is true or false, or whether you can reject or use it. So specifically, null hypothesis is kind of, and you'll see this in the problem. It'll make more sense when I'm showing you an example because it's hard to sort of imagine at the moment. But the null hypothesis kind of looks like this: H0, and then it points to a specific value. The idea that, like, hey, the mean is equal, the mean of the population equal to 40 or 80 years. Maybe that's a scenario. Or the alternative hypothesis, the idea that, hey, if the null isn't true, what is true? Or what is the thing you're trying to prove, basically. The alternative hypothesis is really, this is what you kind of want to prove and what you want to show. And I'll come back to these because this is kind of hard to understand if there's no example here. Second of all, have to understand, first of all, I mentioned before, there's different tests in hypothesis testing, Z testing, T testing, whatever. Depends on the sample you're using, the distribution, and whether the conditions are there. You have to choose one of those tests. And then once you have the test, calculate the test statistic and the p-value. This is where Python comes in, because the test statistic is calculated based on what kind of test you're using. So, hey, I want to do a t-test. There's a specific formula for that. But I don't even need to give you guys the formula because Python has a own command for the t-test where you can plug in the data set, plug in the columns. It'll just give you the test statistic and it'll just give you the p-value. This is what makes your life easy. So really the whole thing here is run one line of code, and the biggest thing you need to know is, one, is my data formatted correctly? And two, do I know what test I'm using? That's it. Once you do that, you can plug it in your code, get your test statistic and your p-value. And once you get these, what this basically means, and you'll see this in, in an example, but really the test statistic helps you calculate your p-value, and your p-value is kind of the thing usually you're looking at. You can also look at the test statistic, but I prefer p-value. And p-value is really the likelihood of getting this test statistic. So let's say there's a scenario out of this scenario. So if the average IQ is 10, not real. If the average IQ is 10, your school did an IQ test. Your school's average is 50. Is your school smarter than the rest of the nation? You're basically, the test statistic that you create is the likely, the one chance that you have, you randomly get your 50 IQ school average based on the 10 IQ national sort of thing. So it's if it's completely random and I'm choosing random things, what's the probability that I could get your, what's the probability that the school completely randomly with their, random IQ of 10, what's the idea that they could get 50? That's probably not very likely at all. And I'll show you this later because you don't see the words in front of you. But really, it's just, hey, if your probability is really small, most likely this wasn't due to chance, and most likely it's significant as a result. Usually if your p-value is less than 0.05, which is called your alpha level or your significance level, basically means that your yeah, your result is significant, and that means you can reject your null hypothesis in favor of your alternative hypothesis, which is usually what you want to prove. And then in that scenario, what you wanted to prove is that your school is smarter than the rest of the nation. So it's kind of stuff like that. So yeah, once you understand that the p-value is less, then you get that conclusion, which is, hey, your school's smarter than the rest of the world. Congrats. Here's a bit more of a explanation onto what I'm talking about when we're looking at like the idea of, p-values and stuff. So if you remember before in the law, the polling and all that stuff, if you saw you had your distribution, um, in the sample, yeah, it's like if you're pulling all these samples, right, you're gonna end up getting these frequencies. It's pretty intuitive, but the idea is really, hey, this it'll usually kind of congregate here, but it's generally a curve. This is like, hey, based on chance, based on this random drawing, this is the kind of shape that you'll end up getting. And this is actually called a normal distribution. Not this one. Yeah, it's called a normal distribution, and it's relatively common in statistics. It's a big population measure, but this is the idea that the entire population, like based on randomness, this is kind of the frequencies where it'll stack up. And in the middle usually is sort of the mean. So like the IQ thing that I showed, usually your 10 would be in the middle because, hey, the average is 10. That's probably your population mean. And then, hey, if your school got 50, you're probably all the way over here, which is like, hey, it's less of a chance that together it created 50 there if it was there. So it'll, yeah, once again showing the example, but I'll get back to this. It's a big thing in statistics to like know distributions. Not going to touch on it too much at the moment. You can check it out later if you want, because I'm kind of short on time at the moment. But it's really, the idea is that, hey, if it's kind of in this extreme area, it's more likely that it wasn't really due to chance that you were, randomly. Like, hey, if you were doing the IQ thing, and it was in the middle, let's say like the national IQ is 10, right? And then your school, it got 11. So that's kind of like right here, right to that inside. Most likely, that's just, hey, someone randomly got a question more right than usual, and that kind of just shifted it a little bit. But really, by chance, if your school itself were to take it over and over and over again, most likely you'd fall into this similar distribution too. And so your school probably doesn't really differ from the national average. But hey, if you have 50, it's really not likely that like every kid suddenly like randomly answered all the questions correctly. It's more likely that your school itself might be more smart. And so it's really, this is usually the threshold. This is the 0.05 that I was talking about. This is the threshold that it's really going to be unlikely that this whole thing was due to chance. So maybe over here, maybe but it's not really a thing. And the reason why these are kind of different is because these are not really different tests, but it's different ways that your your alternative hypothesis is being carried out. You're focusing on different things. And here's what I mean. If you remember before, the H0 represents null hypothesis. So here maybe the context is, hey, H0 equals the mu. So like this mu, by the way, means like mean, like the population mean. Like it might be 0 here. That might be the thing. H0, mu equals 0. That's cool. Here, the idea is that you're like, when you're looking at this thing, you're trying to say, hey, your alternative hypothesis that it means that the mean might be greater than the population average. So here it's like the idea that the 50, for example, that means your school's smarter. That's greater than the average. Here it might be, hey, you just want to look at, hey, is your school dumber than the average? So, maybe you got like -5. That's probably worrying for all of you, but it would kind of show you, hey, you're looking at the other side of the spectrum. Here, you're just looking at, hey, is my school different? Is my school just different from the average? And then this kind of differentiation, they kind of say right tail, left tail here, but really this whole thing is just a one tail test. You're only looking at one tail of the distribution. You're looking at one extreme. So you don't care if it's dumber here. You're just I just want to be smart. It's either we're smart or we're nothing. So it's like you're not really testing for whether it's a that extreme. But here you're just looking at two sides. That's a two-tailed test. We'll come back to this, but it's important to know that basically the only real difference here when you're testing is that when you do it and you get a two-tailed test, you just have to divide your p by 2 in order to get the one-tailed test result. It's the same for both because it's just one distribution, but it's that's kind of what you're trying to aim for. So yeah, here's the example. Here's an example. I think very off with the 10 and 50, whatever I'm doing, but here's a better example. Your school thinks that your kids are smart. They're above average intelligence. So you sampled 30 random students, got a mean of 112.5, and the mean population is 100. So in America, the whole thing, 100 is the general IQ level. And by some miracle, the standard deviation of the population is 15. This is a special case, and I'll explain why in a minute. But yeah, this is a scenario. And basically, if we're looking back at what we're doing, we're trying to say, hey, is this school smart? We're given this thing. Is this school smarter than the 100? Do we have sufficient evidence to support that? So let's try this. Let's try this out. Let's try this out a little bit. Okay, so let's try this. Roy might want to think about this a bit. So first of all, stating the hypotheses. Your accepted population mean. So your null hypothesis, as I mentioned before, it's like stating the value. So here you're thinking, hey, the mean population is 100. So really the null hypothesis is like the thing that is the accepted sort of thing is that, hey, maybe your school is the mean population IQ. So we have no reason to assume that it's not it's not above average, it's not below. We're just assuming on a baseline, all schools have the mean population IQ. That's a reasonable thing to make. So you're trying to say, hey, the population for, it's equal to 100. That is your null hypothesis. So that is the accepted population mean. Alternatively, you want to claim that, hey, students have above average scores in this school. So you're trying to say, hey, if it's above average, you're doing a one-tailed test, you're trying to say your mean is greater than 100. So that is the thing we're trying to prove in a sense. That would be your alternate hypothesis. And null is really just, hey, this is based on chance. The whole scenario that happened based on chance, it's still 100. Your population mean is 100. That's the kind of thing you're working with. So then what this kind of shows you, if you plot this in the distribution that I'm telling you about, hey, 100 is the middle, and then your thing is over here. So maybe if you're looking at the other thing, maybe you could be like, hey, this is extreme. Hey, this doesn't look that extreme. Who knows? This is based on the standard deviation, by the way, that I told you about in 15. So that would kind of give you a visual representation of where this kind of falls. But a lot of people make the mistake where they're like, wow, this looks super extreme. It's probably not. Yeah, it's probably not, but it's not. You can't say it's significantly different yet. You don't have the quantitative grounds to prove that yet. So here's what you have to do. Your second rule is state the test, make sure the conditions. So this is, as I mentioned before, this is a very specific scenario because in the scenario that I described, I have given you, first of all, the mean population and also the population standard deviation. And these very specific conditions mean that I'm allowed to use a z-test here. But the thing is that usually you don't have a population standard deviation. And I'll get to this later on when we're covering t-tests, but the idea is that z-tests are really not that common in modern statistics and real life application, because very rarely are you ever given the population standard deviation unless your population is something very specialized. But it's not the most common test in the world, and it's really only applicable in AP Stats classrooms where they fabricated the scenario and they can give you the standard deviation that they are aware of. So z-tests in general don't feel necessary to retain this knowledge. It's rarely used, and you don't have to remember the formula or how to code it or anything like that. But there's a reason why stats classrooms use it, and it's because it helps you understand the basic theory sort of used in hypothesis testing and the basic scenario that you want to do with it. So it's, once again, not going to be a big focus of the class, and that's why I didn't even put it on the agenda or anything. It's really just a tool to help you understand just this scenario of hypothesis testing. So hey, let's say we use it, the one sample z-test. Good for us. So calculating the test statistic, there's a formula for the z-test, and I don't really think it's necessary to show, especially since you're not even going to use it anyway. So, but if you were to plug it into code or were to plug it into the sort of statistic and calculate it, what you end up getting is a z-score of 4.56 and a p-value, based on the z-score, a p-value like under 0.0001. And if you remember before, if your p-value is less than your alpha level or your significance level, which is 0.05, you can reject the null hypothesis. So if you remember our null hypothesis here, it's that, the mean's just 100. There's no difference between what this, like the school and the population. But hey, apparently the p-value is definitely lower than the alpha level. That means that, hey, this might not be correct. We can reject. This is the language you use usually in statistics. You never say, hey, I'll accept this. I'll accept that hypothesis, because you can never accept a hypothesis. You can't ever solidly say concretely, unless you're really grabbing the population sample, you can't ever really solidly say that your hypothesis is accepted, even in like science at all. In like, Darwin's like theory, I think that's not even like totally proven yet. It's just the thing we're latching on. So Darwin's not accepted. I don't think you guys can accept anything either. But here for now, what you can say is that you can reject the null hypothesis, which basically kind of means rejected it in favor of the alternate hypothesis, or two, you failed to reject the null hypothesis, this thing still holds true, that kind of thing. So the idea is really, hey, if it holds true, which is that, like, if not that holds true, but if it's if you fail to reject the null hypothesis, you're basically saying, hey, this scenario that happened, probably based on chance, nothing that really shows me that this is a significant result that differs from the population, like the population mean or the population proportion, whatever it is, doesn't really differ. Most likely just a chance probability kind of interesting little change from the from the average, but it's most likely still conforms with whatever the population is. So in this case, though, it rejected the null. We were able to reject the null because our p-value was super small. And now what you can kind of say here is that it's probably not due to chance. Maybe the fact that the students got 112.5, I know Roy mentioned, it doesn't look that good. It's probably not that good for a lot of things, but for this test that we used, it kind of, since the p-value was so low, it kind of features the idea that, hey, maybe the people are a bit smart. Maybe they're not that smart. Maybe they're not like 1,000 times smarter, but they're a little bit smarter, at least from the population. They differ enough significantly that we can reject the null. So that's kind of where we're going with this basic scenario. It's the overall idea here. But yeah, I did mention before that okay, first of all, this whole scenario that I just described, that's kind of just the basics. That's just the basics of hypothesis testing. So this, whatever thought process this was, how you conduct the 1, 2, 3, 4 sort of pattern, that is just kind of the universal way that you should go about hypothesis testing. So yeah, that's really the case for this. So really understanding, first of all, how you get your hypotheses, how you can grab your tests, which is what we'll be covering throughout the rest of the class, and how to really, interpret your p-value and interpret how your conclusions are drawn. That's really just the basics of hypothesis testing. That's it. That's the foundation. There's a way you can get really complicated or really simple, but this is just the standard, the standard theory of hypothesis testing. So that would be pretty much it for this example scenario. But I did mention before, there's different tests, right? I mentioned this. There's different tests. When you're choosing your test, you have to choose wisely. You have to think about which variables you're taking a look at. And even though for this foundational example, we use the z-test, we usually never use it because of that standard deviation limitation. So this is what happens here. This is what happens. Instead, we use something called the student t-test, which is like, like in the name, pretty similar to what z-test looks like. But the beauty is really you can use this without that standard deviation limitation, because in real life, you almost never know the population standard deviation. So yeah, I'm going to direct you guys to Colab again. So if you guys remember, first of all, I need you guys to download this bacteria.csv. That's a important thing you should know. And then second of all, I need you guys to go into the hypothesis testing. Yeah, I need you guys to go into the hypothesis testing Colab. So open that bad boy up. We've got like 20 minutes or so. So we should be able to kind of clean this up real fast. So yeah, let's talk about this. Let's talk about the t-test. I personally, big fan of t-test. So not my favorite test, but definitely getting there. Mostly because I don't work as much with the kind of data that it needs. But basically, t-testing, as I mentioned before, you don't need to know about the population standard deviation here. So you don't have to be aware of that. And that was really the biggest limitation with z-test, because otherwise it's a pretty fair test, but it's only really used in statistics classrooms for kids to understand how to do hypothesis testing. So hopefully z-test did help you out a bit there, but otherwise it's not really applicable anywhere. But what we can use instead of the z-test when we're looking at this stuff, we can use the t-test. And so first of all, what's the t-test? The t-test is actually like not that different from the z-test, but it's a method of testing your hypothesis. It's a hypothesis testing technique. It tests your hypothesis specifically about a mean of a sample drawn from a normally distributed population. And you don't need to know the standard deviation once again. And normally distributed population seems fancy as a term, basically just means this, that curve, the way that is normal. There's ways you can check for whether your population is normally distributed. Most of the time it is. Sometimes you'll see like skewed sort of distributions where it's like, hey, like if you're living in a rich neighborhood, you're checking income, most likely skewed to the richer side of things. That might not be normally distributed. But t-test wise, you're really just looking at whether your small sample is drawn from a normally distributed population. And there's specific conditions for this that you can use. Like, for example, there's a sample size restraint. I believe it's over 30 at least for it to be like treated as normally distributed, something like that. You can look those up at your leisure. But really what the t-test is about when you can use it is it's being used to determine, is there a difference between the means of two groups? So, hey, if you have group A, it's like, let's say 20. If you have group B at like 50, is the difference between these means, is it due to random chance, or is it due to there's a real difference that's going on here? And then that lets you kind of look at more things. So it's really, you'll see an example here because I put in something, that's why I had bacteria, but the law of large numbers still really works with this because the idea is that as your sample size increases, your distribution, the t-distribution is basically just the distribution that the t-test works out of. The distribution of the statistic approaches the standard deviation, not the standard deviation, the standard normal distribution. And so yeah, here, if you have a sample size greater than 30, you can just basically assume usually that the normal distribution is a thing. It's like an AP stats thing, and it's a thing to be aware of there. but most of the time t-testing is usually a great way of going about sort of understanding mean differences and the differences between groups. Once again, as I mentioned before, if you remember those two-tail, one-tail tests, t-testing can be either two-sided, so it's two-tailed. So yeah, hey, basically the means just aren't the same. They're just not the same. I don't care if it's higher or lower, it's just they're not the same. Or it could be one-tailed, which is, hey, group B specifically is larger than group A, or group B is smaller than group A, something like that. That's, really the different ways you can test it. So here, if you look at this graphic, what you really kind of get here is the, the distribution for, a mean. And then, as I showed you before, it's really, hey, if it's extreme, it's really close to one of those tails, more likely for it to not be due to chance, more likely for that difference to not be attributed to chance. These symbols, you don't have to know it specifically for coding or anything, but it's always good to know about it. This is the kind of mean for the population. This is the mean for your sample. So it's like, hey, a sample, if you remember the polling thing, this is the, 100,000 people. This is like maybe your sample of 10 that you pulled out, and that's the mean for whatever the sample of 10 was. And so, yeah, once again, least likely, not really likely for it to be due to a chance, difference, just like a chance error or anything. That is the formula to get the test statistic. Once again, don't have to know this. You can search these up if you want, but you'll never, unless you take AV stats, there's no reason for you to have to memorize this if you're doing it in a real world way, since it's really just, you can just use it with code and they already have that down for you. So yeah, here's the assumptions. Is that one, the samples are drawn from their populations, they're representative and they're good. Two, the populations, they're normally distributed. And then three, the populations have the same variance. The sample size is equal for both. So it's not like group A has like 10 million people participating, group B has 5. That's probably not, that's probably not the same in terms of fairness and in really checking that stuff. So yeah, it doesn't have to be perfect. There's sometimes you don't have perfect things, but you try to be as similar in those groups as possible so that really the only difference can be attributed to the groups themselves. That's kind of a general rule of thumb that you want to be aware of. So yeah, 15 minutes less. Let's talk about scenario 1. So if those of you who haven't done that yet, download bacteria.csv. Got to do it for this lesson. So here's our scenario. There is a researcher and you are recording these bacteria counts in water samples sampled from these water fountains at 2 different parks. So you're looking at the same bacteria, you're looking at kind of like the same count, and then you're just getting random samples from 2 water parks. Those are your groups. So you're trying to see, hey, is the mean, contamination in the parks different or is it the same? And, this is probably an important health question because, hey, if it's different in Park B, maybe there's an infestation going on. Maybe it's like dirtier. Maybe you have to clean that up. Maybe there could be health complaints, etc. So it's important to know, hey, is this kind of a normal level or is this, is one of the parks really having issues? Is it struggling? So that's a potential way, that's a potential reason why people might want to be looking at this stuff. But the scenario itself really just boils down to, hey, if we're looking at what t-test does, hey, is the mean of the Park 1, is that different from Park 2? All right, so that's your scenario. Gotta understand that. And once you understand, hey, you're looking at means, you're looking at that stuff, you might want to go to t-test, especially because the counts, these are quantitative things. So, and these are kind of quantitative groups. So that's important for the t-test because I don't think you can do it without that stuff. I know there's different tests for different variables, like chi-square caters to a different kind of batch. ANOVA caters towards specific, the amount of groups you have. This is good for this group where you have 2 groups that you're just kind of comparing the means of. So let's try this out. You guys know this already, set up your environment. There's some extra things in here that you're gonna have to be aware of, specifically using SciPy, I think, and statistics. I think I'll point that out to you when I use those codes, but really, really what happens is that it's just different tests use different like packages. I use this for the t-test because I don't think I found one from NumPy or whatever it didn't really work out that well. Because packages update, packages change. But there's a nice one I found on the statistics package, so I kind of just used it. But yeah, when you guys are doing it, don't memorize, hey, pandas contributes to this, this, and this test. You know, you don't have to know that because you can really just Google, hey, how to do a t-test in Python. It'll give you some code for it. You can try that out. So most of the time, that is usually how a lot of the code comes out from, especially for people who aren't that code heavy or aren't that concentrated on code. Anyway, you guys know the drill here. Upload your file. So if you remember, we got that bacteria.csv file here. So let's see if I can do this. But yeah, remember to upload that. Once again, very UI friendly. For those of you who haven't done it before, you just have to click it, and that's pretty much it. And then make sure to do that. It'll assign that bacteria.csv thing into a data frame. So yeah, I preached at you guys about visualization for like half the class last time, so it'd be a shame if we didn't use it. So let's kind of just approach this like you'd approach a general, you know, this is a brand new data set. You don't know what we're doing with it. Let's take a look at the data frame, you know? So yeah, once again, you can, I don't think this is that big. I always tell you guys, don't do like just, you know, that stuff. So you could try df.head, just take a look at what your first few stuff is. So, hey, you've got two parks. It's Sandusky and Homestead Park. And these are basically the counts. So I think they gave you units up here. Just important to keep in mind when you're actually formally writing a conclusion, but hey, these are basically the counts given from the, different things. So I think it's not that big. Don't do this at home ever, but you can kind of, for those of you who want to just see the whole thing, it's kind of this little table here. So not that big, but don't do this usually. I just can't find the CSV thing to show you guys right now. Anyway, so since we're interested in the means, we might as well graph them, right? We might as well graph the means, see what it looks like visually. Here's what you can do. For me, what I kind of did, you can throw together, there's no actual thing for you to just nicely throw in the columns and gives you means because it's, I don't think any of them work like that. But what I did do, I did a pd.dataframe. So this is pandas, once again. pd.dataframe basically makes new data sets, data frames, anything. So yeah, once you've got, what you've got here is kind of a row for the Homestead Park and the mean of the Homestead Park, which is just created by this function. This mean thing, by the way, is from this. There's no, Python doesn't have a mean, which sucks, because I think that'd be really useful. But yeah, this is from that package, I believe. I had to hunt for it because it was giving me errors like 24/7. But you've got the mean here, and then you can find Sandusky Park and the mean here. And then it'll label your columns, which is like the park name and the mean. And what you get from that, if you run that part, don't worry about the bar plot for now. If you run that part, you're going to get this nice, hey, this is the park, this is the mean of the things. So let's graph that with the bar plot. Basically, hey, this is the data frame, right? You want this row, yeah, you want this column, you want this column, and then this is your X, this is your Y. You want a dark blue color, it's 0.4. Check it out. That is a graph of your two means visualized. And so right off the bat, you can't say anything significant yet. You can't say anything about that. But what you can say is, hey, from a basic visual thing, what do you kind of see? You kind of see, hey, Homestead, larger mean than Sandusky. Seems intuitive, but hey, might be helpful for you if you are trying to determine if you are using a one-tailed test, for example, you could try to specifically cater, hey, I want to look at Homestead is greater than Sandusky. You're not going to say, I want to see if Homestead's smaller than Sandusky. You're just not going to get that period, because even from a visual standpoint, you're not going to see that ever right now. So yeah, helps you look at, first of all, if the means do look different, and whether, you know, you can use what kind of one-tailed test, what kind of one-tailed test conclusion you will be drawing. There are extra things you can do here on a visual basis, especially in error bars. I know if you've seen error bars in some other, like, yeah, if you've seen error bars in other graphs, we're not going to focus on that right now because it's going to be a bit complicated to explain why you're choosing these error graphs or error bars. But yeah, it's these things where it kind of shows you like either the standard error, the standard deviation. Standard error is what's used usually for t-testing purposes, but it kind of gives you an idea like, hey, if these bars are together, even if there's like a difference between these means, those bars are together, most likely like the fact that it's here right now is once again probably due to chance, and that these two might not differ that much in respect to their actual like average levels and anything. But yeah, real fast. Once again, I told you before, if you know the test already, it's really simple to run this. So let's just run through this real fast. If you have a two-tailed t-test, two-tailed, if you remember, is just, hey, are the means different? Are they not different? I don't care. So null hypothesis here is just, you're basically saying the mean of the Sandusky Park bacteria is the same as the mean of the fecal coliform. So if you write that mathematically, it's the mu of the Sandusky equals the mu of the Homestead Park. That's it. And then alternatively, because it's a two-tailed test, you just want to see if it's different, is the mean of the bacteria at Sandusky different from the mean of the Homestead? So it's just mu s, you know, not equal to mu h. So the test itself, because you already got your, you got your hypothesis and everything down, it's really, you're using the stats package here from SciPy, and then it's t-test ind df. So this is the column you're using for the Homestead Park. This is the column from the Sandusky Park in the data set. You're assuming it's an equal variance because, hey, you looked at the samples from before here, and you can kind of see like, hey, they're pretty much lined. One of them isn't that different from the other. So you can go ahead with this. If you run that code, you're going to get two things. You're going to get one, a t-statistic, which for now, just don't bother with right now. If you want to get into it later, feel free to, but it's just kind of another way of determining it. But what this statistic basically helps you give is the p-value, and that's what we're going to be focusing on for the purposes of this class right now. If you look at the p-value, 0.0153. If you remember, we assume an alpha level of 0.05. That is smaller than the alpha level. So what we can do here is reject the null hypothesis in favor of the alternative hypothesis. And so what we're saying is basically the contamination between the park of Sandusky and the park for Homestead, the means of the bacteria there are significantly different. You can put significantly here because you have the quantitative evidence that it is, that you actually have a quantitative difference in the means. But you normally, if you're just looking at this graph, you cannot say significantly. Significantly is a big buzzword. I know in English, we throw it out a lot. It's a big buzzword in statistics, and you have to be careful when you're using it. And here you can say, yeah, it's significantly different because we can reject the null because of this alpha level. So these means of the park bacteria, they're different. That's your two-tailed test. Once again, you can do this for the one-tailed test too. So you saw here already that it's greater. So you can basically try this out. Interesting thing here, I'm sure that there is one. I tried digging along, wasn't really a big thing, but there's actually no, well, there might be, but what I'm trying to say is this. This code that I used, that I dug out from the SciPy package, what it basically, the default is a two-sided t-test. So the default is getting that kind of just, is it different? Is it not? We don't know. That's the default level. And so this p-value is by default pertaining to this two-sided t-test. If you want a one-sided t-test, so like the one-tailed t-test, where your alternative hypothesis is, hey, the mean of the homestead is greater, you just basically, if you remember from the presentation before, it's literally just half of like the, yeah, it's like half of the p-value for the other, for the two-sided. So here, yeah, you can see it, like this is two-tailed, this is one-tailed. It's really just half of the two-tailed. So here, if you're doing it like, yeah, if you're doing it through here, what you basically need to do is just take this segment and divide it by 2. And then that's going to be your p-value for the one-tailed test. So one-tailed test is actually, I think it's easier to like hit your alpha level with because of this. So yeah, usually if this already works, then most likely this is already going to be lower than your alpha level. So here, your one-tailed p-value is going to be smaller than your assumed alpha level. That actually means, hey, yeah, the mean fecal bacteria concentration in Homestead, which was like 1.55, is higher, significantly higher even, than that in Sandusky Park, which had a mean of 107.65. So here, that means, yeah, you can reject the null hypothesis, which is that they're, you know, less than or equal to, basically the opposite of what your alternative is. It's less than or equal to the coliform bacteria in Sandusky. So then since we can reject it, yeah. And then once we ran those two tests, what you can kind of say for this conclusion is that, yeah, the levels of contamination, they're significantly different because of those two-tailed tests that we ran. And more specifically, the mean concentration of the bacteria is higher at Homestead because of the one-tailed test that we ran, which allows us to look at greater than, less than, stuff like that. So yeah, that is pretty much the basics of like hypothesis testing, of t-tests in general. It is a very, it's a very like heavy concept. It's something that you need to really understand to kind of get the rest of this stuff. So feel free to come back to this, to rewatch this and like play around with other things. I know there's other like sets. I'll try to give you guys some like, I know there's different resources online for understanding hypothesis testing. So yeah, I'll send you guys some on the ed, and also I'll put on the day 1 and day 2 recordings onto the ed as soon as I can as well. But yeah, thanks for coming, guys. That should be the end of the class. Don't want to keep you guys for too long since it's 4:30 now. But yeah, have a great day, and I hope to see you guys on Tuesday, same time, where we'll be talking about the chi-square and the ANOVA tests. So yeah, thanks for coming.
Thank you.